All right, thanks a lot. It's really exciting to be here. The energy is amazing around Flink right now, and so it's exciting for us to be involved. The title is a little bit different than what I had in the program, but really it's reflecting the fact that, to be quite honest, we're not quite as far along as developing what we're going to build that I'm describing as I wanted to be. So I'm going to talk about the sort of directions we're exploring more than just show you code, which would be nice to have, but we're not quite there yet. So the outline is I'm going to just briefly talk about why deep learning is important for streaming as opposed to just batch, why it's important for Flink, in my opinion. And then we'll get into various ways of handling training versus inference or scoring or doing recommendations. I'll just use the word inference mostly for that process of actually using the models. Talk a little bit about pragmatics with Flink, and you've probably heard bits and pieces of this all day, and I'll highlight a few of them and maybe a few more that you didn't hear about today. And then just offer some suggestions for where I think deep learning and machine learning should go with Flink. As some of you may know, there's kind of a big discussion right now about where to take machine learning in the Flink context. Okay, so why deep learning for streaming, and why in particular deep learning for Flink? Well, first of all, deep learning is so hot right now. We've all heard about DeepMind, and DL4J is the most popular one for the JVM, TensorFlow, and so forth. I forget where I got the right-hand image. It's in the speaker notes that you can get when I post the slides. And I thought I'd make a few comments just in case you haven't spent much time with deep learning, because it sort of has this mystical air about it, but really it's kind of just a very sophisticated nonlinear model of data. And one of the interesting things about it is it's a way of learning features, or letting the system learn features about your data rather than you doing feature engineering up front. That's one of the big advantages of neural networks in general. And this is just a generic image of doing convolutional networks and deep learning. And of course, the reason streaming is so important right now or so hot right now is, everybody wants to reduce the time between data arrival and information extraction, across a wide range of industries like Internet of Things, financial trading. I had this image in a talk last week in New York. Obviously, they've been doing streaming for a long time for like high-frequency trading, but even you'd be surprised how much of the financial world is still batch-oriented. Maybe some of you wouldn't if you're in that space. But they're trying to just make it more ubiquitous to do stream processing. And I think Flink is really well positioned in both of these cases because it provides the low latency that people expect, but yet it can scale, and that becomes really important over some alternatives. I thought I would say too briefly why we're interested in Flink, in particular at Lightbend. So we're actually building a stack that's basically a curated, integrated solution of open source tools like Flink and Spark and a few others that try to provide just a comprehensive solution for people that just have a wide range of problems. They might have data analysts that still want to write SQL queries. I've heard about Hive several times today, for example, and Spark SQL will help them with that. But they still might need low latency streaming or the kind of very sophisticated semantics that Beam provides. So, this is just a diagram of what's coming. We're going to release this in the fall. And the core of it really is, the backplane of Kafka or some similar, maybe, Pravega that EMC has put out as your sort of backplane for data that's, in a streaming context, and then potentially 4 different streaming engines, including Akka is the middleware that Lightbend has been developing for a long time for, highly distributed concurrent processing of data in a more general context like microservices. But the streaming API is kind of nice for stream processing, but it's not really designed for the scale or the sophistication in terms of semantics that Flink provides. It's more of a complex event processing orientation. So anyway, just briefly to contrast Flink with Spark, like I said, we really love the fact that it can handle high volumes at low latency, and the fact that it's really ahead of the game in terms of giving us the kind of semantics that Beam has defined. I don't know if you went to the Beam talk today, but they just keep pushing the envelope And as far as I know, unless you're running Beam and Google Dataflow, Flink is the best choice for running those kind of sophisticated data flows in other contexts. We still think there's a place for Spark, though, because it does give you, just this broad ecosystem that, meets a lot of different needs from, like batch processing, data analytics, data warehousing, that kind of stuff. It is ahead in terms of machine learning and the sophistication of its SQL engine. But it's a mini-batch model, so it's not so great for low latency. And there's even been talks today that talked about how just the performance tends to be a lot better when you're doing true streaming versus mini-batch processing, aside from just the latency that you have to tolerate in the mini-batch case. Okay, so what does it mean to do deep learning in the context of Flink? A couple of things I think are worth considering. First of all, it depends on how you're going to do it. Like, if you're actually okay with starting with a statically trained model, static is in the sense of I might use TensorFlow, like Aaron was talking about earlier today, train the model, export the model through one of several means, and then import it and use it at real time to score data. That actually, I wanted to be clear, it's not straightforward, it's not easy necessarily, but it's a lot easier than some of the other alternatives we'll discuss in a second. But it's a really nice approach, especially if, most of the time you don't necessarily have to have like really up-to-date models. Like spam doesn't evolve that fast. Your trading models, if you're in finance, you may want to, be able to tweak them fairly quickly, but the actual underlying models don't need to be, moving with, or being changed very frequently. So you could even have a situation where you decide, once a day is good enough, so this is what I'm going to do. I'm going to set up a mechanism to import a new model daily, or just restart my Flink job. If it's in finance, you can just redo it. You've got like 16 hours when the trading day is not going on, roughly speaking. So you might just restart your streaming job with a new model every day or something like that. So you just have a lot of options when the model doesn't need to change while the stream is running. But there are cases, though, where you actually do need to do training, even if it's not every single event kind of updates, but, I'd need the model to evolve during the day as the world is changing around me. Then we need to figure out a way to do that training and be able to serve data with the latest available model. So there'll always be this lag. You're actually always using an old model, but it won't be, too long. Now, I say here that most of the time you probably can't tolerate the time it takes to train a model per event and still maintain your low latency. The nice thing about a tool like Flink is you can certainly have dual processing even in the same job. Well, I'll diagram this a little bit in a minute. So I might be scoring very quickly, but then have window functions that are longer, maybe based on triggers or something that are still scoring the data, but they don't have the same kind of latency SLAs or whatever for just doing inference on the data. I don't want to butcher this guy's name, but this talk earlier was really interesting, talking about the performance of low latency. Yeah. I really enjoyed that talk and in particular, he had some really interesting graphs, performance graphs of the kind of penalty you pay doing mini batch stream processing, just in terms of overhead, especially if your data is coming in so fast that you're actually kind of slowing down a little bit, like your Spark mini batch intervals are too short. Anyway. It was a good talk. I recommend you check it out. Okay, so what can we do if we want to train the model and do inference? And let's suppose that online training, and I'll define these terms in a minute. But anyway, training on every record is too slow. I can't afford to do this. Well, there's this idea that you might train in mini batches. And I'm actually misusing the word mini batch, but I'll define it more carefully in a minute, where I'm just going to grab a bunch of records, some window, and then I'll just do a batch training session, perhaps starting with my existing model and iteratively improving it with these mini batches so that I've got this longer window of latency. Then I've got this problem, though. How am I going to update the model that I'm actually using to score data to do inference? Even though at the same time that I'm doing this training, I could also be taking whatever the old model is and doing inference on that. Another problem you run into is that because we're talking about Flink, we're talking about a distributed system. So now I have to worry about, I've actually got data that's partitioned. So I've never actually have all of the data visible at one time. So, how do I keep my partitions in sync? And they actually talked about this in the earlier talk as well. Well, it turns out there are ways to do this. There's actually some theoretical work that Deep Learning for J exploits where you can actually train in parameters in parallel. They'll be slightly out of sync, but if you average them, it turns out that you generally get really good results. So I used to do physics a long time ago, which is why I have gray hair. And what they do is just get little tricks like this all the time. There's this stuff in high energy physics where they do these really amazing calculations, and they get these infinities that just happen to cancel out, and everyone says, okay, let's just go with it. And that's sort of what we do here. We often don't know quite why these things work. For example, none of these models are truly convex, and yet it seems like convex techniques generally get us to maybe not the globally optimal solution, but close enough. And this is another example of that, actually, where theoretically it seems sound and it seems to work to just average the parameters off of these different partitions so that we kind of keep things in sync, even though they tend to diverge as one partition of my data is getting one set of data and being trained on that, and other partitions being trained on a different set. Okay, let's dive into this just a little bit more about the kinds of training we might do and then how we might serve this. So there are really three terms that people use that kind of represent a spectrum. The original way that we always did training of any sort of data before we came up with fancy words like deep learning was, I just have this big batch of data, I'll train it all at once. That's a pretty classic thing. We all did this in like high school chemistry where we did experiments and we fit a line to the data. We were basically doing batch training of our model in a sense. This new idea is mini-batch training, and I just misused it deliberately a minute ago because it's now being thought of in two different ways. The original way was, what if I have a machine learning model like a neural network that has thousands of parameters, and I actually am fortunate enough to have a lot of data, and now I have these gigantic matrices that I have to do linear algebra with, and it's too expensive. So they came up with this idea, well, what if we just trained samples at a time? Samples with replacement, meaning I could actually see the same data over and over again, and some data I may not actually ever sample, but nevertheless, I'm working on the same batch, really, but I'm just taking it in small chunks at a time and iteratively training the model. And it turns out this actually works quite well, and it does get around this performance problem. Now, the way that I just misused the term mini-batch that you're also seeing people use is the idea of, well, if I have a window of records, whether it's in Spark mini-batch processing or Flink windowing, is that a mini-batch in the same sense that I'm training a model? And technically, it's not the same thing because it's not the same data that I'm sampling from. I'm actually getting new data. The rationale for it is, well, maybe that's the best way to get optimal performance of the system, especially if I'm going to be training with GPUs where I don't want to send a record at a time. I want to send like a chunk of, records at a time. But I have not been able to find, and if anyone has found this, let me know. I haven't found any theoretical work that justifies this assumption that we can actually use the same approach on data that isn't being replaced in the sample, that we're actually always training on new data. I think it should work because we're pretty happy with this alternative idea, that the other end of the spectrum, which is online training, where we're literally just iterating the model in every single event. So, for example, you may have heard of stochastic gradient descent, where on every record I'm just going to make a correction, and it'll just sort of like walk around the space and eventually work its way to a near optimal solution. And that also, again, works reasonably well in practice, even though sometimes it's a bit sketchy theoretically. So we do have this sort of spectrum here, and we are kind of using mini-batching in even more maybe a nebulous way of thinking about whether we can do it on streams or not. But so far it seems to be working for people, and I hope that there'll be some theoretical work that justifies convergence or whatever. Again, the advantage also would be that if the world is changing around us, then we kind of would like to have a model that's slowly tracking the way the world is going and deprecating the influence of older data. Well, if you want to learn more about online training, go to Trevor Grant's talk right after mine. A little shout out to fellow Chicagoan here. He's going to go into this in more depth. Okay, let's get back to Flink then and talk about some practical approaches here. And what I want to start with first are actually general design approaches that aren't necessarily specific to Flink, but I think are particularly relevant when you're talking about this problem in Flink. So one way you might do it is if you have a machine learning library that you're calling in the same processes. And I tried to illustrate that because it's a distributed system, it could actually be a bunch of different tasks, each of which has this library linked in. But as the data stream goes through, I'm going to have basically the tasks both handle scoring and training in some way. But we do have this issue of, well, how are we going to share model parameters between things? I already mentioned one possibility is that we have a way of exchanging updates between these partitions, then we do model or parameter averaging or something like that. But there needs to be some mechanism to do that, or otherwise these tasks, the parameters in each task will grow out of sync over time. Another extension of this idea would be, whoa, sorry. What if we actually have separate services that we're calling? We actually pass the data out to a service. Let's assume for the sake of argument at the moment that we're going to both do this asynchronously for scoring, for doing inference as well as training. I'll talk about the async IO API in just a second just as an example of how we might do this. You can imagine a hybrid solution, though, that you call out to the service to do training, and then you somehow export the model to do in-process inference for even lower latency, so you don't take the hit of an asynchronous call. So, for example, I don't think that Aaron explored this with EMC yet, but he basically trained the model statically, exported it, and then ran it in process inside Flink as part of like a map step inside a Flink job. Could you do the same thing, though, with sort of a mini-batch model, where you keep exporting the model, somehow ingest it into Flink, so that you're constantly up to date in some sense? But the training is actually happening in a separate process, separate from this inference process. Another possibility is that you actually run separate jobs for both training and for scoring, as I call it in the diagram, or inference. I don't really think this is that necessary because it's easy enough to write this kind of separation inside just one Flink job and let Flink figure out how to schedule things in this way so that your inference is still fairly fast while you might be doing windowing over the data for mini-batch training, for example. I also didn't keep sketching all the alternatives. Here I'm just showing calling out to services, but you could certainly use the library approach for this as well. And then finally, another possibility that we're exploring with our platform is, what if you really want to use Spark to do training, but you want to do scoring with Flink or inference with Flink? So once again, you'll need a way, probably this time you really would have to use separate services to share the model between the two systems. But this is another idea we're exploring, and we'd like our platform, our fast data platform, to make this easy for customers to do if they really want to do it this way. There is one other way you can do it, and that is rely on the cache. So we have these distributed caches like Alexio, which used to be called Tachyon, or Hazelcast, or EHCache, any of these. Where, and what I really like about this idea is that you sort of virtualize the notion of where the actual model parameters are, and you let the cache worry about keeping things in sync between them. Now, there's a little bit of a hit because you're kind of giving up some awareness of where data actually resides. So it might be that if I'm doing a low latency scoring process and the cache infrastructure detects that, however it does it, that its model parameters are out of date, it might actually delay that performance while it goes and fetches around the cluster the latest model parameters. But nonetheless, this would at least give you the illusion that everything's all just in one place, and that might actually be an advantage. And the usual rule is true that you don't want to do premature optimization because it just complicates the code in general. Okay, and then to just drill down a little bit more into model serving and some options there. there's actually been a lot of work, both academic and just industrial work, on so-called parameter servers, or different names around them. And the idea is that, imagine I really do have a huge distributed job that's doing training, and I need to move parameters between these tasks very efficiently and quickly. This ND for J, it comes with deep learning for J. TensorFlow has its own serving system for this purpose. There's a Berkeley project, the same sort of hotbed of innovation that created Spark in the first place, and tools around it like Alluxio and Mesos for that matter. They have this new prediction engine they're building called Clipper that's designed to be highly optimal for this. And Prediction.io is another one you might have heard of. Sorry about the coughing. And just on a little bit more on deep learning for J. Actually, let me just get a little water here. Now, one of the attractions of this thing for Flink is it's also JVM-based, so it's a little bit easier to interoperate with it, either as a library or using, as a separate server, so it doesn't really matter. It could be TensorFlow for that matter. There was a talk about it last year at the German Flink Forward that you might want to look at. Basically, it was kind of a lot of experimental attempts to integrate DL4J's DataVec format, which is kind of designed to make it easy to do ETL with your data, to get it into a format that the engine can use. I think this is a good direction to go, and I hope that this gets completed, but as far as I know, no one's actually finished or open sourced this. So let's dive even deeper into Flink features that we could use to help implement all this stuff. One of the interesting new ones that's being developed is called side inputs. So we've had side outputs for a while, where I have the main line of stream processing, and then on the side I send data out of the system somehow. And now they're working on sort of the dual case, which is I actually want to get data into the system. And the classic scenario would be just what we're describing. I want to slowly update my model parameters while I have this fire hose of data flowing through the system. How could I possibly do this? And in our case, this is really an ideal scenario for our case. It's not the only reason they're thinking about side inputs, but it's one possibility. And now an interesting case comes about then. Well, okay, so I've got this data coming into my streaming job. What do I do with these parameters? How do I actually use them? How do I do inference with the new parameters coming in? Am I basically doing a join? Does that make any sense? I think the answer here actually is to use something like the co-flat map operation or co-group operation. So if you were in the talk in the room just before ours from Better Cloud, they were talking about using this to join two different, like a control stream and a data stream. This is the same thing you could apply here. I don't have an example of that particular thing, but I'll show you an example of side inputs in a second. There are a couple of other decisions that have to be made, and these are factors that are going into the design of this. One is, would this data somehow be keyed, that is the model parameters, with the data that's flowing through the system, or would it just sort of be general broadcast data that is independent of the stream? And related is, am I doing this over Windows, which sort of implies that the model parameters I'm sending in apply to a certain set of data in the window, or is it more global? I think the answer in most cases is going to be it's just broadcast data, it's just global, it's not actually related to anything in the stream itself. But you could imagine some scenarios where you try to decompose things in a more fine-grained level, perhaps because you're trying to run some really massive jobs, and it actually makes sense to have slightly different models for subsets of the data. Like, I'm only going to recommend these kind of things for a customer to do if they happen to be in a given geographic region or something like that. I think this is an area where there's going to be a lot of experimentation that would be worth doing to see how you could actually use this kind of partitioning from keys and windowing to reduce the amount of data that you're trying to join together in some sense. So here's a sketch of what it would look like, and I basically stole an example right out of the design documents on the wiki and rewrote them in Scala because I'm a Scala bigot, and then changed the names a little bit to give a sense for what it might look like to pull this data in from the side for model parameters And once it's in, then you could do something like a co-flat map or co-group operation to get it into the model and then score data against it, or do inference. So you basically have two data streams, one being your data fire hose, the other being your model. You set up this singleton side input is the name of the class here that you would use to construct the stream, or the way of getting data into the model stream. And then you would just do a regular map operation for the intention of scoring this data. But periodically you'd get model parameters coming in through the side stream, and then you could output a score on based on running that through the model to do inference, and then return a new tuple with the record and its label or score. So this is sort of the gist of how it would look. It's, again, it's not too complicated. The hard part is actually implementing side input, which isn't quite done yet. But once it's there, then I think we have a real opportunity here to leverage that for doing training on the fly, even training outside of this current job. I mentioned also there's side output, but sort of a dual operation we could try is, rather than having the data pushed into us in some sense through side input, what if we actually went out and asked for it using the new async I/O operation, which would let us multitask requests for data, and while we continue to process, and then when the result comes back, then we can use it. I'm not exactly sure how this would work in this case, because it sort of implies that I'm going to ask for model parameters that apply to data, and only when the model parameters come back am I actually going to score that data. That doesn't quite make sense. So I'm just mostly mentioning this as an option for thought, but I'm not entirely sure how it would work in this case. The idea, though, would be it would be nice as a way of periodically polling for new data, like maybe every minute we think it's frequently enough to ask, so have you got any changes to the model parameters, and then get it that way. But on the other hand, it might not be the most efficient way to do it. And like I say, it sort of implies a join operation that doesn't quite make sense yet. So this is something I want to think some more about. But schematically, it'd look a little something like this. If I can get back to the right slide here. Try this again. So what I've done here is just taken another example and sort of massaged it into a way that you might abstract over what kind of modeling environment you're using, whether it's TensorFlow, deep learning for J, or whatever, and then just have something that encapsulates the notion of model parameters. The crucial point here is I have it extend iterable of param, because it turns out we'll need to be able to iterate through the results. So I wanted it to be something that's basically functions like a collection. And then you define this, you basically extend this type called async function, where I'm the first type in the two type parameters. One, I'm just using string to represent a key from just on the assumption that maybe I have several models in flight, and so I want to somehow request which model I'm interested in. And then the params object, again, holding that thing. And let me make sure I don't go too fast here. Yeah, so the next thing would be I set up some client that understands it's sort of an abstraction around the kind of model that we're working with. Again, deep learning for J or something that I need to make a call to asynchronously. So that's why there's a host and port here that I might need to talk to. So this would be like a typical REST request. And then I need to get the executor from the environment. And then the last bit is this method where we invoke asynchronously a request for this given key representing the model I care about. I want to get back a collection of these parameters. And we use Java Futures for this so that it operates asynchronously on a thread pool. This code executes very quickly, but the actual call out could take hopefully not more than a few hundred milliseconds. And then there's a callback that's registered so that if it successfully returns, then we process the results. In this case, I just actually wrote it down on the stream, which doesn't quite make sense. What I would probably do is make a call to update the parameters in my internal model representation. And then subsequent to this code would be a process of actually applying it for inference. Okay, so let me wrap up with just a few comments of where I think we should think about taking Flink in both just the general machine learning, but also the deep learning context. So as you may know, if you follow the mailing list, the current API is mostly oriented towards offline batch training, and it's been a little quiet. There hasn't been much work on FlinkML, the machine learning library. So there's been a recent interest in all right, what should we really do? And there's various threads of investigation that are starting. So there's a link here to the Google Doc that's kind of the sort of the organizer for what people are thinking about doing. And the main themes that seem to be emerging is very interesting is, well, first of all, let's not try to do everything Spark does. That's not our strength. Let's focus on getting offline training working really well, but using streaming instead of batch. Let's think about ways to support online training. And then let's even think about building a model server that's optimized for Flink performance. And actually, one of the engineers on my team is leading that effort. So my recommendation is first, really focus on getting the third-party integrations solid, like Deep Learning for J, like TensorFlow, like the project Aaron has worked on. And some of these others that have been mentioned, like H2O is a really nice system for JVM-based deep learning. And Trevor's been working on Mahout, so I had to throw out a little call out for Mahout. There's a couple of interesting core capabilities that would really help any of these efforts to succeed. One is to be able to delegate work to GPU. So there's an active effort being made to do that, and that's obviously really important for training deep learning models. And then here's the overall link for side inputs that's in process. And I would also just get rid of anything that isn't solid, deprecate it and then just get it out of the way rather than let it be a liability. The last few things I would suggest is there was some discussion about using PMML. I don't think that's really been very successful in the industry overall, and so I wouldn't really focus on it unless there's a true demand for it. Also, Apache Samoa appears to be somewhat dead, so I wouldn't pursue that one anymore either, nor would I reinvent things that you can get from third parties. Okay, so that's basically it. If you have any questions or want to talk to me offline, I welcome email or hate tweets or whatever. And if you want to learn more about this thing we're building, there's a link to the Fast Data platform. Thank you. Questions? Yeah, Joe.
Why would I sideload parameters rather than starting a new job?
Why would I sideload parameters rather than starting a new job with the new parameter set? I think I would actually investigate all options like that. And there's a couple of reasons why you might want to do one or the other. First of all, I actually do like the idea of running more jobs because in general, anything that's going to run for a long time, like a typical streaming job, you're going to see every possible thing happen at some point. Everything from network partitions to spikes in traffic. So you could actually see better performance. Like if you don't really need anything shorter than like a minute or 5 minutes, then should you use streaming at all? You could just make the case that cron is your friend, and I'm just going to run something every minute, a batch job. Other than that, though, one advantage of using side inputs is at least you have all of the code in one place, and it's kind of managed as one job rather than having several jobs. So if you have several jobs running, you'd have to figure out how to get the information back and forth, right? Whereas if I just have one Flink job and it figures out how to decompose everything in some sense, then I don't have to think about it too hard. So that's probably the main reason I would try to do it in one place. Do I need to create or run the Lightbend platform? Yes, you do actually. No, so the reason that's there is because I screwed up and used the wrong slide. No, it does actually run. We picked DCOS because you can run it in the cloud or on premise, and you don't even Amazon, Azure, wherever, and you don't have to know what's actually underneath that. The reason it says Cray is I was at a conference in New York last week where we did a joint talk with Cray. They have some really amazing these stacks that they sell that they're basically regular commodity hardware except for the optical backplane that gives them incredible performance. So that's good eye. Thanks for calling that out, Chip. Yes. Yeah, that's a really good question. Why not just use another Kafka topic for the control plane? Yeah. You know, I was going to add that actually, because that is one of the ideas we're thinking about, especially in this case where I've got Kafka in here. Why don't I just write the model parameters to Kafka and just suck them in like it would regular data? And I think that's a really good approach. So, in fact, that would probably be safer than trying to use a new feature like site inputs that were just put into the main line or whatever. Yeah, so I should have put that in. I should have, yeah. All right, I'm 0 for 2 here, 0 for 3, or 1 for 3. Anyway, do you have another question? I have, to be honest, I haven't used them a lot in Anger. I know that Databricks is working pretty hard on the TensorFlow and Spark plugin. Yeah, you know, the problem with TensorFlow, or maybe the advantage is it's like the sexy thing now, and so everyone's using it. Okay. Okay. Yeah,
Just a general methodology of connecting to Spark.
Yeah. You know, I didn't really call that out too much, but I was going to suggest that the integration with DL4J and Spark is pretty thin, and it would be easy to steal that and port it over to Flink. And so I think the same thing would make sense for these other engines as well. Obviously, there are going to be some differences, but especially because you don't have to be extremely low latency, you can still use kind of the same concepts of Windows to do that. So, yeah, so if I didn't repeat the question, there's been integrations with Spark and a bunch of machine learning libraries. I would just take those and copy them and do them for Flink as well. Anybody else? We're almost at time. But. All right. There's one in the back, and maybe that'll be last. Go ahead. So what's the future of Akka streams compared to Flink? So the way I would think of it is Akka streams was really built with an orientation towards general microservices, and that kind of implies complex event processing. Now, you can do complex event processing in Flink as well, but Flink is more oriented towards data stream processing. It's kind of a subtle distinction. It's more like a Venn diagram of overlap, I would say. What I like about Akka in this particular case, and Akka streams is just a veneer over Akka itself, is it's very lightweight per event. So if you don't have a lot of traffic, but you need to handle each event in a very different way, it's really nice for that kind of low overhead per event, as opposed to being low overhead when you aggregate and amortize over a lot of events. So that's one advantage. It does have more connectivity and more clustering options at a much finer grain level than Flink. So, you know, Flink, like Spark, is really kind of oriented towards a big data problem, and hence the optimizations tend to be focused on how do I optimize the use of big pipes. Whereas Akka was always built sort of from the ground up in kind of let's call it an old school way of, I actually don't have a big data problem, I have a complex small data problem. And so in that sense, I think Akka streams makes a lot of sense, but there's definitely some overlap there. Okay, thank you very much. Yeah.